Good day, my name is Engineer Jason and welcome to my channel. Today we're going to be answering a very important question in structural designs: why 225 by 225 columns fail in construction of multi-story buildings. The cross-sectional area of 225 by 225 millimeter is very common, especially in my country here, but when not used properly, failure is imminent. In this video, we are going to explain why the 225 by 225 columns fail in multi-story building constructions using basic structural principles. So, there are 5 principles in engineering I want to talk about in this video that would explain why this cross-sectional area fails in design of multi-story building. Firstly, I'll stick with basic down to the ignored and I'll start with axial load accumulation. First, the obvious question: that why are columns used and what do columns carry? So a column is a structural member itself that transfers loads from the superstructure down to the substructure, that is the foundation. So a column does not just carry one floor. A column carries the slabs, the beams, and the self-weight of the initial column members above it. So if we're looking at this building right here, we can see a slab here that is going to transfer its load, self-weight, life load, dead load, down to this beam. This beam will carry it down to this column. So this column will carry all the load it has carried down to this column. This does the same thing to this column, and finally to the ground floor column, that is taking it to the foundation, meaning that this ground floor column is carrying all the load up here. For a multi-story building of 4, 5, 6 floors, by looking at it, you will surely expect failure, because you cannot just keep increasing the demand of a structure without adequately increasing the cross-sectional area. There needs to be a balance in the axial load being accumulated and the specific size of the column needed to carry that load. You cannot carry 100 kg and put it on top a very, let me say, a very small boy. Let's go with an age of 10 to 9 years, and you're expecting the young child to be able to move and sustain that load. It's not done anywhere. So keep that in mind. As the demand increases, the capacity cannot stay the same. If it does, failure is imminent. If, for example, during construction of the project, the structural engineer has given out the drawing, it has been vetted, everything certified and ready for construction, but whereas during construction the owner of the structure decides that I do not want this anymore, I want something bigger, I want something better, whereas the processes to get that done are skipped because of they all believe it's just repetition. So if it can carry this, is the same frame, it can carry an extra, without taking into consideration that the more you increase the story, the more you are increasing the load. The second reason why 225 by 225 columns fail is on the cross-sectional area. Yes, I know I'm making reference back to the cross-sectional area because it's really small. A small section means that there's going to be less concrete, there's going to be limited reinforcement, and there's going to be a very low load resistance. Keep that in mind. All this means one thing, that the column would reach its crushing limit in a very early stage. There will be no time for deformation. It will be an instantaneous failure. No time to carry people to safety. It's just going down, and it's going down. Okay, let's look at this. Let's take this column for example. Yes, on that section design. And let's wait for the load. Okay, so we can see that this column surely failed. And what's the cross-sectional area we're looking at here? We are looking at 225 by 225. Okay, so let's increase the cross-sectional area to 300 by 300. I'll recommend that for multi-story buildings. I'll always use 225 by 450 because it's more safer. It gives time for deformation before failure. It does not just happen instantaneously. There's always an assurance that something can be done before failure. So let's look at this. Okay, so we can see it's giving us a go ahead. See, it's passed. So we can see how increasing the section of the column actually helps to increase the strength and actually helps to increase the resistance on the load resistance on the column. So the next point is slenderness and buckling. This reason is one of the most reasons that is normally ignored, because as a building height increases, the column length also increases. The long columns are unstable. If we carry a very thin boy, that's like, let's give him 6'5", okay, and we put a bag of cement on his head. He has no muscle, he's skinny, he's slender, okay, he's skinny. So, and we also give that same 50 bag of cement on top someone that is bulky, is within, let's say, 5'9", 6", has more strength, has more stamina. We'll see that the person we gave the first bag of cement will be wiggling as he's moving. There is no stability. He's an unstable structure. So that's what we see here, because long columns are unstable, short columns are stable. When you have a long column, we are always thinking of slenderness of that column. So 225 by 225 columns have low stiffness, so they buckle easy. So we're increasing the height of the story, we're also increasing the height of the column. Bulking is not a strength failure. Let's keep that in mind also. It's part of an instability failure. So we can see, let's take wind load is pushing on the transverse axis, and the column is not strong enough to resist that. Buckling will surely occur. The fourth reason that I would like to emphasize on is that right from the textbooks, we always assume that columns are under axial loads only, but in real life scenarios that's not the case. It's never the case, because columns also carry bending from their structural from the structural members they are opposed upon. So small columns like 225 by 225 will lose its capacity rapidly under that combination. So let's say we are not taking into consideration axial loads alone, because eccentricity is another factor that we also need to look into, and wind load is another factor that we also need to look into. So you can't just make a design based on axial loads that you expect the column to carry, because structural members are also releasing moments that will have to go somewhere, whereas the column is also taking this moment, taking the axial load and taking wind load with other structural criteria needed. Um, the the next point is concrete confinement. Many people completely ignore concrete confinement. Concrete is very good in compression. Always have that in mind, and it always wants to expand sideways because of the tension. It's very bad when it comes to tension. That's why we have reinforcements and links, stirrups to restrain this expansion. That restraint that you are seeing, we are talking about, it's what we call as confinement. So concrete is very strong in compression but very brittle. Without confinement, once the crack starts, failure is very sudden. Confinement on its own increases the strength of the column. Let's take that. The ductility and the warning before failure. This is very important. The warning before failure. This deformation does not happen in one day. It shows signs before failure. 225 by 225 columns are actually very poor when it comes to concrete confinement, because their size is limited. The corner bars will be poorly constrained. There will be very little space for closely spaced links. Once crushing starts, failure becomes sudden and brittle. So there's no time to even, as I said, there's no time for deformation. It just happens instantaneously. Last point I would like to talk about is construction practices. After the design is made, we have standard design practices, standard construction practices. So once this is ignored, no adequate concrete covers, there is medium, whereas the reinforcements would be shown, there will be corrosion, there will be increase in mass of the reinforcements in the columns, causing expansion. Mind you, concrete is only good in compression and not tension. Once you pull it apart, it will pull apart. Those type of things cause failure. Once we have a good, and we stick to it, a good construction practice, there will be a reduction in column failures. Apart from that, we also have scenarios that I actually explained earlier, of you being on site and adding additional stories on top a building that is only supposed to carry about 2 to 3 stories. You are adding additional 2 to make it 4 stories. There's surely going to be failure, because that cross-sectional area was not designed to carry that load. So all these criteria need to be put into consideration to avoid the failure of 2 to 5 columns in construction. Well, there you have it. I hope this video was able to help you, educate you. For our next video, we are going to be story building from start to finish. So get ready, subscribe, like, drop your comments. I want your comments. I want to see what you guys think. Let's build this community together. My name is Engineer Jason, and see you guys in the next video.